All right, today we're going to be looking at exponential word problems, and specifically we're going to be looking at, and we're really focusing on exponential word problems today, and specifically we're going to be looking at a bunch of different setups. This is a homework, but I think it's worthwhile me walking you through about half of them, and then half of them you doing all on your own within this play posit. So let's look at the first one. Brad invested $2,400 in an account that pays 4% compounded annually. That means at the end of each year. How much will he have after 13 years? So what function should we use that represents this initial setup? Before we get to the question, okay, how much will he have in 13 years? We'll get to that in a second. But we want to we want to set up the function first. So hopefully you can see that it's the amount he has will equal how much he started with times, if it pays 4%, we always multiply by 1 to get him back to how much he was at, and then we add in that 4%, and 4 divided by 100 is 0.04, and so we've got 1.04. Multiplying by 1 to get you 2,400 plus 4% more to go up. Now that's how much we're multiplying by each year, every year. Annually, at the end of each year, we will multiply by that amount, so it'll be to the t power where t is years. Okay, so that's the function. How much will he have after 13 years? It's asking how much will he have. Is that asking for t or the amount? Well, how much will he have is the amount. It's asking for what a is equal to. So what a is equal to after 13 years. That's the number of years. So t is 13. So how much will he have? You do need a calculator for today. You absolutely need a calculator. If you don't have one, you can go to our main blend page and click the calculator icon to download one there. So we're going to put in 13 for the number of years, and hopefully you were able to do that. And with money, we usually want to round to the nearest penny. So we're going to do 2,400 times 1.04 to the 13th power. And there's a bunch of ways you could type that in. Now notice, we're going to round to the penny, but we'll always look at one decimal place after. And since this number is above 5, we will round up. So instead of 17 cents, it'll be 18 cents. So he will have $3,996. And remember, we're going to round up here, and 18 cents after 13 years. That's nice, right? Like, Brad didn't do anything. Maybe he worked. Maybe he has a job that he made $2,400, and then 13 years later, it's just worth $4,000. He didn't do anything extra to get that extra $1,600. He just waited, and it became that much money. By the way, you can get way more than 4%, so you can do better than this. All right, let's look at a second one. It's a little bit different. And I'm not sure we've actually seen a setup like this before, so I'll walk you through it. Sally invested $2,300 in a bond that pays 14% interest. So this looks like normal, like what we've done before. But this part is new. Every 2 years, I want to walk you through this. So it's the amount she has, will be the how much she started with, and it's going to pay 14% interest. So what's the multiplier? Well, it's going to multiply by 1.14, but it's not doing it every year. It's every 2 years. And this is a little bit weird. To find out how many times it's going to multiply by 14%, we need to take the number of years and divide it by 2. Because let's say it's been 10 years. Well, is it going to multiply by 1.14 10 times? No, it's only going to multiply by 1.14 5 times, because it only multiplies by this every other year, every 2 years. And so the way we do this in a formula is we take the time and we divide it by 2 when it says it does it every 2 years. So if there's a constant multiplier every some number of years, we multiply by it, but we divide the time by however often it's doing it, so that we only have it double the right amount of times, or multiply by 1.14 the right amount of times. Okay, from here, how long will it take? So what's that asking for? Is that asking for the amount or the time? Well, it's asking for the time. The time is what we're looking for here. How long will it take for her investment to triple? So that means her initial investment is going to multiply by 3. Her investment was that $2,300 she started with, and we want that to triple. So what we're going to do is we're going to take that initial $2,300 and we're going to multiply it by 3 to find out this is what we want her money to get up to. We can use a calculator here if we want. $6,900. So it says, how long will it take for the amount to be $6,900, and we got this because it said it wanted her investment, which was $2,300, to triple, which means multiplied by 3. So I want you to solve it from here. How long will it take? And hopefully you noticed you should put in 6,900 here. And this is an exponential equation. We want to get the exponential part by itself, so we divide by 2,300, and when we divide by 2,300 on both sides, oh man, my calculator might run out of batteries today. That would be embarrassing if that happened in the middle of this video. So 3, when we divide 6,900 by 2,300, we get 3. And now we have an exponential. So to undo this exponential, we need to do a log. We need to do a log with a base of whatever the exponential is. So log base 1.14. And the way to do this in most of the calculators I showed you is to press the math button. You press math, and we're going to scroll down to where it says log. Log base is right here. Another way you can get to it is a little faster is press math and then up twice. Get you there faster. Log base 1.14 of 3. So we get, I'm only going to round to 2 decimal places for now, but that's because I'm not done with the problem. When I finish the problem, I won't use this number. I will use the exact number that's in my calculator. So to undo dividing by 2, so that canceled out the exponential. To undo dividing by 2, we multiply by 2. Now notice, I'm not doing 2 times 8.38. This would be bad. This is not accurate enough. Instead, I want to do 2 times, and I want to go up and highlight this exact number. And I'm going to end up rounding at the end to 3 decimal places. So for times, we're going to round to 3 decimal places. Time is 16.769 years. That's how long it takes for her investment to triple. Okay. If we wanted to, we could convert these 0.769 into days. So we could say 16 years. And how can we find how many days this is? Well, we take the rest part, the decimal part, 0.769. I guess we can take 0.887 and multiply it by, that's this part of a year, and we can multiply it by 365 to see how many days it is. So 16 years and 281 days. If we wanted to change it to days, we could take that decimal part and convert it to days by multiplying by 365. All right, one more I'm going to walk through with you, and then you're going to get to try one completely on your own. A certain material decays. That means it goes away. Hopefully we've learned about this in chemistry. A certain material decays at a rate of 1.9% per year. Okay, the sample is 260 grams. So this is the starting amount. How much will be left in 11 years? So what is the setup for this? What is the, before we get to the 11 years, what is the setup for what's actually happening here? Well, the amount there is going to equal how much we started with, 260, times, now this is a little tricky. We always multiply by 1 to get us back to our starting amount, and we're going to subtract 1.9% because it's decaying. It means it's going down by 1.9%. So 1.9% divided by 100 is 0.019. We moved the decimal place twice. So we're going to move the decimal place once and twice. So we need a 0 there. So 0.019. And so if I do 1 minus that, that's 0.981. So more commonly, we would write this as 260 times 0.981 to the t power, because it's every year. So every year it's doing that. So t is measured in years, and here's our thing. So you can solve it from here, I think. How much will be left in 11 years? And hopefully we notice by now, this is the time. So the time is 11 years. How much will be left is what we're looking for. So we're going to find what a is equal to after 11 years. So a is 260 times 0.981 to the 11. 260 times 0.981 to the 11 power. Oops. And the answer is 210.539. We go to 3 decimal places for time usually, and notice that it was an 8, but the next number is above 5, so we round up. Okay, let's look at this next one. You're going to do this all on your own. Read it to yourself and try to answer the question. So if you didn't get it, Amy bought a diamond ring for $6,000. That's how much it started at. The value of the ring increases at a constant rate of 5.8% per year. So let's write an equation for this. The amount is going to be how much it started with times 1 plus 5.8% divided by 100 is 0.058. 1.058. We move the decimal place 2 times to the t because it's every year. So it's going by that. How much will it be worth in 21 years? That's t is 21. And so we're going to just plug in 6,000 times 1.058 to the 21. This is money. This is going to be a money amount. So the amount is going to be $19,604. And since it's money, we round to 2 decimal places because that's pennies. We always round to 2 decimal places in monies. 0.25, the next number is lower than 5, so we don't use it. All right, another one I'm going to do with you, and then you're going to get to do a bunch on your own in a row. A bacteria population doubles every 8 minutes. The population begins with 1 cell. How long will it take to get to 512 cells? You can we'll use a calculator on this. Okay. If that bacteria population doubles means it is multiplying by 2 every 8 minutes. That's another one of those structures we saw earlier. So the amount is going to be, it said it started with 1 cell, that's the initial amount, times it's multiplying by 2, that's what doubling is. And it's going to do it every 8 minutes. So it's not to the t power. We're going to have to take however many minutes it is and divide that by 8 because that's how often it's doubling. So like if it is 24 minutes, it'll double 3 times because 24 divided by 8 is 3, and it will only double 3 times once every 8 minutes. And we want to know when it will grow to 512 cells. So 512 is equal to, when you have 1 times something, you can just ignore the 1. Also, you could divide by 1 on both sides. That also wouldn't do anything. That would be fine. All right. So what should we do next? Hopefully we realize we should do log base 2 on both sides because this is an exponential and we want to get rid of it. 2 to what power equals 512? You can do this in a calculator. Math, I actually know the answer is going to be 9 because I know my powers of 2, but you are not supposed to know that necessarily. Math, log base, so math, log base 2 of 512. 2 to what power gets you 512? And the answer should be 9. Okay, so 9 equals t divided by 8. And how do we undo dividing by 8? Well, we multiply by 8. So t is going to be 72. Now, let's say what units this is. It's doubling every 8 minutes, so this is 72 minutes. And if we wanted to, we could take 60 minutes out to make it 1 hour. So 1 hour and 12 minutes. That's another way we might want to write our answer. Okay, Greg bought a gold coin for $9,000. You can do this on your own, guys. Do this on your own. If you had trouble with it, let's go over it. Greg bought a gold coin for $9,000. That's the starting amount. The value of the coin increases at a constant rate of 12% every 5 years. So it's going to be multiplying by 1.12. We're going to move the decimal place 2 times, 0.12, to the, it's only doing that every 5 years. So it's to the t over 5 power. How many years will it take for the coin to be worth $20,000? So that's what the amount is going to be. So we want $20,000 to equal 9,000 times 1.12 to the t over 5. We're going to solve this exponential equation. First, we get the exponential by itself by dividing by 9,000 because the exponential is being multiplied by 9,000. And I'm just going to leave that as 20/9. You could divide it out if you wanted to, but I'm going to leave it as a fraction. Seems a little bit easier. The reason I got this is I knew 3 zeros would cancel from the top and from the bottom, so there's still 1 0 left on top and no zeros left on the bottom. Now, to undo the exponential, we need to do log base 1.12. And I need to do that in a calculator. I certainly cannot do that by hand. So math, up, log base 1.12 of 20/9. So 7.05 is what I'm going to write here, but I'm not going to actually use that number. I'm going to use the exact number. Now I need to multiply by 5 on both sides. So 5 times that answer. I'm not going to use 7.05 that I wrote down. I'm going to use the exact number up above. And the answer is t equals 35.2 3. I don't need to put a 0. Notice the number after, so I wanted to go to 3 decimal places, so 229, but the number after the 9 is a 7, and the 7, when it rounds up, will make the 9 turn into a 10, so the 9 will go up to make this one 3 afterwards. And you don't need to put a 0 afterwards when you're rounding. So that's my rounding tip for you right there. Even though I wanted to round to 3 decimal places, I don't put 0 because of how it rounded. Okay, so, and I guess I should say what unit this is in, since it's a word problem. This is the number of years. T is measured in years. Okay, great. Try this one on your own, guys. Albert, if you didn't get it, let's go over it. But pay attention because you should be getting these by now. Albert currently pays $400 premium for his health insurance. Yikes. If the premium increases at an annual rate of 2.5% per year, boy, guys, if health insurance only increased at 2.5% per year, I would love it, but it increases way faster than that. How many years will it take for the premium to be $800? So his premium right now is $400. So the amount of the premium is $400 right now. And every year, annual rate means every year, it's going up by 2.5%. So we need to move the decimal place twice. So we'll need a 0 here. So it's multiplying by 1. And then we're adding in 0.025. And it's doing that every year. How many years? So we're looking for what T is going to equal to get to $800. So let's see, $800 is the amount we want to get to. We need to get the exponential by itself, so we divide by 400. Dividing both sides gives you 2. To undo this, we need to do a log. This is going to need to be in a calculator. Math, log base, 1.025 of 2. So we're doing the log base with whatever the exponential is, 1.025. And that is what T is. So T is now by itself. T is 28.071. I'm going to round to 3 decimal places, and this is measured in years. In word problems, we really should use units. Notice I used years, hours and minutes, or minutes. Here, this was money, so I put a $sign there. Here, I didn't, but I probably should have. This is measured in years, so I should have put years. Days, years, whatever. So in word problems, we want to put units. Try this one on your own. Francis created a chart showing that the population of a town will increase to 95,285 people from a current population of 11,210 people. But she forgot to include how long it will take to grow to this level. Well, that's important information. She does know that the population increases by 4.2% every 3 years. Be careful here. How many years will it take to grow to 95,285? So the starting amount is this. So the starting amount of the population here, I'm going to use P equal for population. A is the more general amount. If you put A equals, it's okay. So the starting amount is 11,210. And that is getting multiplied by, the multiplier is 1 to get you back to where you were, and it's 4.2%. So we need to move the decimal place twice. So 0.042, we're adding that into 1 to make it grow by 4.2%, but it's every 3 years. So it's not doing it every year. We have to take the number of years and divide it by 3 to see how many times it's actually going to multiply by this. So like if it's been 30 years, right, it's only multiplying by this 10 times because, it's only doing it every 3 years. It'll multiply by this 10 times. So we take the number of years and divide by 3. And we want to know when that will grow. So this is P equals this. When will the population be this? And how many years is asking for what T is equal to. So we're solving for T, and we're going to plug in for P. So 95,285 equals 11,210 times 1.042 to the T over 3. We're going to divide by this. Let's go ahead and do that in the calculator. 95,285 divided by 11,210 is 8.5. Oh, that's nice. 8.5 equals 1.042 to the T over 3. This is getting a little bit messy. Sorry, guys. And now, to undo an exponential, I need to do a log. So log base 1.042 on both sides. So math up. Log base 1.042 of 8.5 is 52.02, but I'm rounding this in the middle of the problem, so I won't actually use this number when I type it in the calculator. Equals, I don't have t by itself, that's t over 3. To cancel out dividing by 3, I need to multiply by 3. And again, I'm not actually multiplying this 52.02. I'm going to use the exact number from up there. So 3 times this is 156, sorry, 0.05. That's what t is. Usually I would round time to, this is in years? Yes, how many years? Every 3 years it's doing this. Usually I would round to 3 decimal places for time, but notice that it's 0.049. And when I look at the number after the 9, it's a number that's bigger than 5, so that 9 rounds up, and it makes this other 9 round up, and it'll go to 50. But I don't need to put a 0 on the end. So 156.05. I guess if we were in science, we could indicate that we know a number of significant digits by putting 050, but we're not doing that here. I'm going to do this one with you guys because I think this one's a little different. So the number of bacteria in a culture grows from 38 to 171 in 49 minutes. So this is the time, and this is how much it grew from. How many bacteria will be present in 2 hours? Now, it doesn't say this here, but bacteria grow exponentially. So bacteria grow exponentially is like the common model for it. It is how a lot of things in nature grow. And so how many bacteria will be present in 2 hours? Well, I need to develop a model for what's happening here. What is the constant multiplier? I'm going to consider the 38 to be my starting amount. So I'm going to say the amount is going to be 38 times something to the t, but I don't know what this multiplier is. And so what I'm going to do is I'm going to use the other information to figure out what my multiplier is. And there's a couple ways. Okay, well, let's do this. So it's 171. The amount will be 171 after the time is 41 minutes. So I'm going to put in 171 will be 38 times some rate. I don't know what the multiplier is to the 49. And what I'm going to do is I'm going to solve to find the rate using this initial information. So I'm going to divide by 38 to get the r to the 49th by itself. So 171 divided by 38. So 4.5 equals r to the 49th power. This is not an exponential. It's not a number to an exponent to a variable. It's a variable to a number. So this is like if it's r squared. You don't do a log to cancel out r squared. You do a square root. If you have something to the 3rd power, you do the cube root. If you have something to the 49th power to solve it, we are going to do the 49th root. And we're going to do that on both sides. Let me show you where that is in your calculator. You're going to press math. That's where a lot of like special functions are. You press math, and there is a star button here to do any root. So it says do any root, and we're going to choose what root we do. We're going to do the 49th root of, here we're going to pick this number from up above, 4.5. So the answer is that the rate is 1.031. This is not our answer to the problem. The problem didn't ask what rate was it growing at. But what we did here was we used the initial, we knew it had to be growing exponentially, so we knew it had to have a constant multiplier every minute. We just didn't know what it was. Then we used our information to figure out what the rate was. So now we've got our rate, and we can go back to this initial problem and say that our model is going to be the amount of bacteria, is going to be the 38 it started with, times the rate is 1.031 to the t. Now I can tell you how many bacteria will be present in 2 hours. But we have to be a little bit careful. T does not equal 2, because remember, the time we were using here was minutes. And so if we had minutes up above, this 2 hours, we need to convert to minutes. 2 hours is 2 times 60 gives you 120 minutes, and that's what we need to plug in here. So this was a tough problem, I thought. So 38 times, I'm going to use this exact number, not what I wrote down here, to the 120, and we get a population of this. Now, I notice I rounded up the 9, rounded up. Oh, wait, hold on. 7, 7. I rounded that wrong. It's bad. 7, 7, 7. Okay. The 9 rounds up to make a 7. I want to show you that we could have done this a slightly different way, which is, I think, neat. That we could have done it a different way. Again, we could think of our initial model as, okay, there's 38, and it multiplies times something to the t, where t is minutes. So t was in minutes. Another way I could think about it is that we start with 38, and it's multiplying times some other rate every 49 minutes. Every 49 minutes, it will multiply by this rate. So I'm going to put t over 49, and this would be another way I could solve it, although it would be harder this way. So there's a few different ways you could do it. You could think about it as exponential growth. So, this is maybe the easiest way to do it. I could think of this as continuous exponential growth, which is a reasonable thing to do with bacteria. So I could say that the population will be 38 times e to the RT. Man, this is how I should have done it to begin with. And this way it's going to be easier. And the population will be 171 when the time is 49. So 38e to the r times 49. Again, we would need to solve for r. So when we divide by 38, we get 4.5 equals e to the 49r. And to undo e, we would do natural log of both sides. So, natural log of 4.5. That's how we undo e to the power of something. It's a log with a base of e. You could type log base e if you wanted to, but this way is way faster. And so now we would get 1.5 equals 49r, and we can find r by dividing by 49. So 1.5 divided by 49. Notice this r came out to be, oh wait, I shouldn't be, what did I do wrong here, guys? I should not have typed in 1.5. I should type in this exact number divided by 49. And it'll make a slight change. Notice that, like, if I round to 3 decimal places, 4 decimal places will be slightly different. So 0.031 is what I'm going to write down here. But when I go back to my initial problem, p equals 38, e to the rate is 0.031, t. Now when I say 2 hours, and again, this time I was measuring was in minutes, so I still need to put in 120. 38 times e to the point, I'm not going to write what I had there. I'm going to use this exact number, times 120, and I get the same answer as before, 1511.777. So I could use a continuous growth model, or I could use a, there's just some constant multiplier that's a rate model, and it'll come out with the same answer either way. Both came out to be 1511.777. So that's kind of neat that you can do problems different ways. All right, Peter is growing. You guys can do this on your own. Peter's growing bacteria in a culture dish. Initially, the population was 135 per square centimeter. The population triples every 2 hours, so multiplies by 3 every 2 hours. When will the population reach 10,000? Okay, so the amount of bacteria is 135 times 3 is the constant multiplier. That's what tripling means. And it'll do it every 2 hours. And we want to know when that will be 10,000. When will the amount be 10,000? And so we want to find what the time is that will give us that. So we are going to divide to get the exponential by itself. So we're dividing by 135. So 74.074 equals 3 to the t over 2. To undo exponential, we do log base, so math up. Log base 3 of 74. Oh my goodness. Log base 3, let's make sure I'm actually typing it in right, of 74.0. Nope, I shouldn't type in 74.074. I should use the exact number from up above. Don't round in the middle of a problem. So 3.919 I'm rounding when I write it down on the paper because I don't want to write out all these numbers. But when I actually use the number in my calculator, the last thing to do to cancel out dividing by 2 is multiplying by 2. And so I will multiply this exact answer by 2, and I will get that the time is 7.837, and this is measured in hours. That's how long, man, that is not very long for it to take for it to go from 135 bacteria to 10,000. Okay, try this next one on your own. In 1989, Linda was able to get oil and a filter change for $20. In 1999, that same oil and filter costs $28. Assuming that the inflation rate remains constant, how much will it cost to have the same maintenance done on the car in 2011? So we need to set up an exponential model because the inflation is remaining constant. The rate of growth, the constant multiplier, is remaining constant. So I'm going to use the continuous growth model, P e to the RT. So the amount, the cost, I guess, is going to be the $20 it started with times e to the, it doesn't tell us what the R is, RT. And what we're going to do is we're going to say, look, I know that after some number of time, so how much time passed here going from 1989 to 1999? Well, the time is 10 years. 1999 minus 1989 is 10 years. So 10 years passed, and when 10 years passed, the amount went up to 28. I can use this information to solve for R. So 28 equals 20 e to the 10R, and I'll be able to find what R is this way. This is just like number 9 that we did together a little while ago. So 28 divided by 20 to get the exponential by itself. 1.4 equals e to the 10R. To undo e to the power of, we do natural log. It's this ln button. Natural log is really easy to get to. Natural log of 1.4 is 0.336 equals 10R. And we're going to divide by 10. So we're going to take that exact answer and divide it by 10. R is 0.0336. And so now, that's not what it's asking for. It's not asking what is the rate. It's asking how much will it cost in 2011. So I'm going to take this R and plug it back into my model. I found out what the rate would be, the rate of growth is. And now I can say that the amount is 20 e to the 0.0336 t. And so I can see how much time passes from when it was $20 to 2011. So it was $20 in 1989. How much time is passing between 2011 and 1989? Well, 2011 minus 1989 is 22 years. So time will be 22 years. And that's how much time it will take to grow from $20. Notice I'm not using 1999 here because that's when the cost was $28. So the amount will equal 20 times e to the 0.0336 times 22. I'm just going to type that in. 20 times e to the power of is right above the natural log button. You get to it by pressing second. E to the, and I'm going to use this exact rate, times 22. And the answer is it will cost $41.92. So A equals $41.92. And I round to the nearest penny when it's money. I want to point out that if it's growing at a constant rate, I could have used 28 as my starting amount, but then it wouldn't grow for 22 years. It's only growing, if it goes from 1999 to 2011, that's only 12 years. So I could have done this by starting with 28 and doing it for 12 years, and that will come out with the same answer, which is kind of neat. All right, guys, I'm going to do this one with you. ATVs were bought at the same time. One ATV cost $10,000 and depreciates 22% yearly. The other ATV costs $8,000 and depreciates by 18% yearly. Determine the number of years it will take for the two ATVs to be of equal values. So I've got one function. The amount for the ATV for the first one is $10,000 and it depreciates. It means it's going down by 22% each year. The second amount is $8,000 and it goes down by 18% each year. And I want these to be equal to each other. When will they be of equal value? I want to find the time that will make them be the same. So I can set these two equations equal to each other. First one is 0.78, and the second one is 8,000 times 0.82 to the t. Now this one's a little bit different because there's two different exponentials. We need to get a single exponential together, and we need to use a property of exponentials here, which is that a to the x over b to the x is equal to a over b all to the x power, because fractions, when you multiply them out, the tops all multiply times the tops and the bottoms all multiply times the bottoms. So what I can do is I can divide both sides. I'm going to divide by 8,000. So 10,000 divided by 8,000. I'm going to do on the left side. So 10,000 divided by 8,000 is 1.25, and I'm going to divide by 0.78 to the t to move this to the other side. So I'm dividing by 0.78 to the t on both sides. And I'm also dividing by 8,000 on both sides. Now, this can be combined into a single exponential. So 1.25 equals, this is 0.82 over 0.78 all to the t power. So 0.82 divided by 0.78 all to the t power. This is 1.058, so 1.25 equals 1.05 to the t. And now I can do the log base on both sides. So math log base, and I'm going to use that exact number, not a rounded version, of 1.25. Oops. And so the answer is t equals 4.462 years. Okay. In 1995, you guys can do this on your own. In 1995, the population of Tangent Town was 4,350. In 2006, the population was 5,600. How long will it take for the population to double? So hopefully you realize this is one of those ones where we have to find the rate it's growing by. So last time I did the exponential model. This time I think I'll just do a rate model. So let's see. It started, the amount, or I guess the population, is equal to 4,350. That's the starting amount. And that will multiply times some rate to the t power. Okay, so this is an exponential model. I could have used a continuous growth one where I did e to the rt, and that might have been a little bit easier, but I'm going to do it this way for now. And I know that the population will be 5,600 after a certain amount of time has passed, after 11 years has passed. So when 11 years has passed, the population will be 5,600, and I can plug in that p and that t to find out what the rate is. So 5,600 equals 4,350 times r to the 11. I'm going to divide both sides by 4,350. And 1.287 equals r to the 11th power. This is not an exponential. We will not do a log here. This is a variable to a power. If it was 11 to the r, we would do log base 11 on both sides. That's if there's an exponent that's a variable. That's an exponential. This is something to the 11th power. It's a power rule. And so we need to undo the 11th power, we do the 11th root. So the 11th root on both sides. And to get to that, we press math. The 11th root of, I'm going to use this exact number, is 1.023. And I'm going to plug that back into my original equation. So the population is 4,350 times 1.023 to the t, where t is measured in years. And now it says, how long will it take for the population to double? So how long will it take? We're going to be looking for what t is equal to for the population to double. Population doubling means times 2. So the initial population was 4,350. So to find when it doubles, that's the same as finding when we multiply it by 2. So the new population will be 8,700 equals 4,350 times 1.023 to the t power. I'm going to divide by this, and that will give me 2. 023 to the t. And I'm going to do the log on both sides. So you guys can't see this. I divided by 4,350, got 2. Now I need to do a log. So math log base 1.023 of 2. And so t equals 30.482 years. So guys, I just want to point out that, when we have a variable to a number, to cancel this out, this is the 11th power, so we do a root. When we have a number to a variable, this is an exponential, and so we do a log. So we do logs when the base is a number, and we do a root when the base is a variable. All right, let's do this one together. There's some slight difference here. A material decays at a rate of 0.0084% per year. So to convert this, we're going to still need to move that decimal place 2 points. How long will the material take? How long will it take? Man, this is really poorly phrased. How long will it take so that only 43% of the original material is left? Okay, so the amount is something. They didn't tell us what the initial amount is. That's what's different about this one. I'm going to call the initial amount C for some constant. I don't know what it is. There's some constant amount that it starts with, and that's getting multiplied by 0.01. We have to move this 2 places. So this is going to be, when we divide by 100, it's going to be 0.00084. There's going to be 2 extra zeros when we move it to the t, okay? Now what we want is for there to only be 43% of the original material. This is the original, C is the original amount, and we want to end up with only 43% of the original amount. So that's going to be 0.43 times C. That's how we find 0.43%. That's the ending amount, right? We don't know what the starting amount is, but we know that we want to end with 0.43 times that. And so that's what I'm going to plug in here for my A. 0.43 C equals C times 1.00084 to the t. It turns out you don't need to know how much it started with, because when we try to get the exponential by itself, we will divide by C. And when we divide by C, the multiplying by C and dividing by C will cancel out, and we get 0.43 equals 1.00084 to the t. And finally, you can get this. We can get math log base 1.00084 of 0.43. Uh-oh. Aha. Well, guys, it said it decayed. I know it's, so let's just look. I know that the answer is not, it takes negative 1,000 years. So either the problem's wrong or I made a mistake. It said the material decayed at an amount of 0.084%. And so instead of adding 1, I should have subtracted 0.0084. And so this exponential is not 1 point that, it's 1 minus 0.00084. And that is the rate that I'm supposed to do the log of, 0.99916. So I'm going to change this to math log base of 0.99916 of 0.43. And now it tells me that the time is 1,004.304 years. So notice, like, when you're doing word problems, you want to think, does something make sense? Does it make sense for it to be a negative amount of years? Not really. And that material was decaying, so I found my mistake was that I should have been subtracting instead of adding. We all make mistakes, but one thing we get good at as we get better at math is like noticing when you made a mistake by figuring out if something makes sense. Last one, do it on your own. A local government projects that its town will grow at a constant rate of 37% per year. At this rate, how many years will it take the town's population to be 6 times its current size? Okay, so a local government projects that its town will grow at a constant rate of 37% per year. Okay, again, it didn't tell us the starting amount, but it doesn't matter. The amount is going to be some starting population times 1.37 to the t power. We don't know what the starting population is, so I'm going to put a constant in there. And we want it to grow to be 6 times the current size. So the current size, the starting amount, is c. We don't know what it started at, but we want it to grow to be 6 times c. That's what we want the amount to grow to be. So I'm going to plug in 6 times that current amount over here. And I hope you were able to figure that out based on our last problem. So we don't know the starting amount, but we know it needs to grow to 6 times that amount. And so when we divide by c, you'll notice that c will cancel out on both sides, and we won't have that variable anymore. It turns out it does not matter what that starting amount is. You're going to do log base 1.37 on both sides. So math log base 1.37 of 6. And the answer is t equals 5.692 years. We're going to round to 3 decimal places. Okay? Guys, I want to point out that some of these other ones where it said, how long will it take to double? We doubled the initial population, but it turns out we could have put any number there. Like you could have put 5 or 70 or 1,000. Any number that you start with, it will still take the same amount of time to double because that's how constant multipliers work. So even though we had a number there, it could have been a different number and the answer would have come out the same because, when you multiply by 2 and then divide by that thing, it ends up with just the 2 there. So that happened in a few of our problems. I don't know if you noticed it. All right, that's all for today. This was an extremely long play posit compared to what we've been doing this semester. So, I hope you feel good about it. Have a good day.